If we were to attempt this one in rectangular coordinates, you see on this figure, if we were to take a look at everything to the left of this line, any vertical rectangle would be going from the inner circle to the outer circle. However, over on the right side of the line, vertical rectangles would be going from the y-axis to the outer circle. This is not a type 1, and you can verify it is also not a type 2. So that means you would have to set up two separate integrals, and that's just for finding the mass. Then you still have to do 2 for finding the moment about x and 2 for finding the moment about y. That's not going to be too cool. So we're going to do this in polar coordinates. So to do this in polar coordinates, notice that here on our region, this is perfectly fine for doing dr d theta or d theta dr. It doesn't matter one way or the other, because thetas are going from 0 to pi over 2. And r's are going from the inner circle to the outer circle, which for ours would be 3 to 7. Now, likely as not, in your problem, you're going to have different values here. But I think we all are going to have the thetas going from 0 to 2 pi over 2. But when we set up our double integral, we've got to have the component r, because we always have the component r. That's how the polar integrals are defined. So now we need to transform the function, the density function, into polars. The bottom is pretty straightforward. X squared plus y squared is r squared. Now the top, if you recall, x is the same as r times the cosine of theta. Now there's a lot of things that will cancel here. We've got this r times this r, which is r squared over r squared, so they're going to disappear. And I'll go ahead and rewrite this. So we'll have a double integral, and our integrand will just be the cosine of theta. Now the values. If I'm going r's first, that would be 3 to 7. Then thetas, 0 to pi over 2. Now I can evaluate that with my TI-89 fairly quickly, although this is not such a hard thing to do by hand. And then we come down to the moment about the x-axis. Now remember, the moment about the x-axis means the distance from the x-axis vertically to some point in the region. And that distance is what we call y. So we have to take our integral for mass, and we have to multiply the integrand by y. Well, obviously, since we're in polar coordinates, we can't use y, so we'll use something that y is equal to, which is r times the sine of theta. And so now we need to do that integral. And again, we can do this by hand. It's going to take a little longer. Or we can do it on our TI-80, which comes out to be a 10. Likewise, the moment about the y is that same mass integral that we started with. But we have to put an x in here, and for x we will use r cosine theta. And then evaluate that integral. And so now we're ready for our center of mass. Now again, to keep these straight, you can always go back and look at your picture and think about how we developed these. The x coordinate for the center of mass needs to involve the x distance, which happens to be the m sub y. Now, I know these letters don't match up, but again, you can memorize all of that or you can just reason it out. And so we've already done those calculations. And likewise, the y coordinate. And I'm pretty sure they would want that simplified. So while we're here, let's see about this. Now remember, the x bar and y bar we have here are in rectangular coordinates. And so the 5 pi over 4 is about a 3.9, and the 5 has is exactly 2.5. But with that said, the center of mass of this is 3.9. Now this was 3, this was 7, so somewhere in here it was 4, 5, and 6. So 3.9 would be right here, and 2.5, this is 3, so 2.5 would be just below the 3, would be right there. So you can see that's about right in there, which it's a good sign if that point falls within our shaded region.